Hey guys, my name is Stephanie LaGrone and I am actually the science supervisor for the district. But before I was a science supervisor, I was a chemistry teacher for a very long time. So I'm super excited to get to share what is actually my favorite 6 weeks of chemistry with you guys. We get to talk about chemical reactions, we get to talk in a few weeks about this thing called the mole, and then we get to the end with something really, really cool and awesome called stoichiometry. So hang in with me for the next 6 weeks on Wednesdays at 1:30 and we will have some chemistry fun. So today we are going to start our topic off with chemical reactions. Okay, so chemical reactions are just when you take the atoms of two things and you put them together and you kind of mix them up in a blender and they rearrange and form something new. So a chemical reaction is when you take stuff and basically you form new stuff. Okay? Now you've heard of this before. You may not have heard it called a chemical reaction, but what you have heard it called is a chemical change. So actually last quarter in chemistry, you guys talked about chemical changes and physical changes. So when you talked about chemical changes, you were really talking about chemical reactions. So some of those examples for some chemical changes that you guys talked about were probably burning, tarnishing, digesting, rusting. So it's something where you take one substance and you transform it into a completely new substance. For example, when you burn a piece of paper, it is not a piece of paper anymore. When you eat a cheeseburger, after it's digested, it is not a cheeseburger anymore. So all of those are examples of chemical changes, which you now know are called chemical reactions. So there's a couple ways that we can tell if a chemical reaction has occurred. The first way is if you have a change in temperature. If something gets hotter or something gets colder, that's some good evidence that you've had a chemical reaction occur. You can also have a change in color, which we're actually going to see in just a minute. We're going to take two colorless things, mix them together, and get something that's bright yellow. So when you have a color change, that's indication that you've had a chemical reaction. You can also form a solid. When you form a solid in a chemical reaction, that's called a precipitate. Okay? You can also form a gas. And when you form a gas, some evidence for that would be bubbles. So when you mix two things together and bubbles start forming, you know that you've had a chemical reaction. Another one is you can have a change in smell. There's actually a lab that I used to do in AP chemistry and organic chemistry where we make something called esters. And it's where you take two things that smell really, really horrible. You put them together, you let them react with a little bit of heat, and when you take the film off the top of the test tube, all of a sudden the lab is filled with the smell of bananas. So you take two things that smell really, really bad and you turn them into things that smell really, really good. So what I'm going to do now is I'm going to show you a couple of examples of what a chemical reaction would look like. The first thing is a change in temperature. If you're doing a change in temperature, that's like, think of your hot packs or your cold packs. I always think of the hot hands that you break apart and you put in your pockets to kind of keep you warm. That's actually a chemical reaction that's happening. You can also have a change in color, which is what I'm going to do now. I'm actually going to take two chemicals, which if I show you, I want to kind of hold them up in front of some white paper to show you that these things are actually colorless. They don't have a color to them right now. So what I'm going to do is put a little bit of this one chemical into here. And you can see that this is, again, actually colorless. There's no color to it. And I'm going to hold it up in front of some paper so you can actually see the color change. Now I'm going to add this other chemical that's also colorless. And when you put them together, you see a bright yellow color change. So you have a bright yellow in here. And this also, not only did it have a color change, this, if I let this sit here for a little while, you'll see that this actually formed a solid. The solid will actually sink to the bottom of that test tube, and you'll have two distinct layers. Another thing you can have is you can form a gas. So what I'm going to do right now is put a little bit, this is just baking soda, put a little bit of baking soda into a test tube. And then I'm just going to add an acid. You can do this one at home if you want to take some baking soda, make sure you have parents' permission. Take some baking soda and add an acid. An acid that you could use would be vinegar. You could use lemon juice. Any kind of homemade acid you have at home, or home acid that you might have in your refrigerator. I would do vinegar. So when I click on here, when I drop this in, what you see is that we have bubbles forming. And when you form bubbles, that's an indication that you have a gas. You've created a gas, which is one thing that we look at when we're trying to figure out if we have a chemical reaction or not. Now, a few minutes ago, we said that there were some things that you had talked about chemical changes before that were chemical reactions. And one of those things was burning. Next week, we're going to talk about these reactions. I'm not going to actually tell you what the chemicals are. And we're going to go over the formulas for them, and we're going to talk about a special kind of reaction called a combustion reaction. But I want to show you right now how if you have a change in temperature or you burn something, that is also going to be a chemical change. So I want to show you that right now because I was told I needed to have a little bit of fire. What I'm going to do first is pull my hair back and put my safety goggles on because safety first. So I'm going to take something that's actually a flammable compressed gas. Do not do this at home. Leave this to the professionals, otherwise known as your friendly neighborhood chemistry teacher. And what I'm going to do is stick my hand in. And that is an example of a chemical reaction. So I promised you fire. You got a little bit of fire today, and I promise you we're going to have some more of that next week. So what we're going to talk about now is how to write these things, okay? The way chemists figure out what's happening in a reaction is they use a chemical equation, okay? But you need to know some definitions before we get moving. So one of the first definitions you need to know is a reactant. And I'm going to try to beat these into your head today. A reactant is a substance that undergoes a chemical reaction. The way I like to say that is it's the stuff you start with. So the reactants are the things that you start with. Now when you're looking at a chemical reaction, reactants are always going to be on the left side of the arrow. So what are the things we get? The things we get are called products. Products are going to be on the right side of the arrow, and they're the things that you produce, the new things that you make, the new substances that we get. So I want to show you kind of what that looks like. When you have a chemical reaction, this is kind of the format that you're going to see. You're going to see the reactants on the left, right here. And then you're going to see the products, which are the substances that you produce. You're going to see those on the right. Well, what if you have more than one reactant, and what if you have more than one product? You separate reactant from another reactant, or product from another product, by using a plus sign. And when you're reading that, just like you would read it in math, it means and. So anytime you see a plus sign, or you're going to read that as the word and. Now, you're also going to see an arrow. An arrow, like right here, is what separates the products and the reactants. So you're going to see that the reactants are always going to be on the left. They're going to be separated by plus signs if there's more than one. Your products are always going to be on the right. They'll also be separated by plus signs if there's more than one. But to separate reactants from products, we're going to use that arrow. And that arrow is going to be read as goes to give, or yields, or produces. So some other things that you need to know when you're writing chemical equations are some symbols. When you see an S in parentheses, that means that that substance is a solid. When you see an L in parentheses, that means that substance is a liquid. Sorry, my hand is touching the board. When you see a G, that means we have a gas. And when you see an AQ, that means that substance is actually dissolved in water. That means aqueous. Now I want to hit a misconception right here. A lot of people get liquids and aqueous confused. So I want to talk about something you're familiar with at home. I'm going to talk about salt, NaCl. If I wanted NaCl, sodium chloride, liquid, I would have to take that solid salt that's in your salt shaker and I would have to heat it so hot that the actual solid salt melted and became liquid NaCl. That's different from NaCl aqueous. Do you know what this is? Don't forget aqueous means dissolved in water. This is just good old salt water. So just because it's in a liquid form or you see water as a liquid, that doesn't mean that these two things are the same. This is the actual pure solid that's been heated to a point where it melts and it forms a liquid. And then this is when you take that same chemical as a solid and you dissolve it in water. So we're going to use these different states when we write our reactions. So the first way to express any kind of chemical equation is by using words, using a word reaction. So this is an example of a word equation. It is solid iron and chlorine gas react to produce solid iron 3 chloride. So what's wrong with this? This is a great way to talk about a chemical reaction. The problem with this is we chemists, we don't have a lot of time on our hands. We like things short and sweet. And this is really, really a lot to write. So we had to come up with a way to take all of these words and convert them into something that's much more condensed. And we do that by writing what's called a skeleton equation. So a skeleton equation takes those words that you just saw and it converts them into chemical formulas with those little pluses and arrows that we just talked about a minute ago. And you get a nice condensed shorthand version of a word equation. But there's a couple things you have to know that you're going to get stuck on. If you can't do these, it's hard to move forward to do these skeleton equations. The first thing you have to do, and you learned this last quarter, is you have to be able to take the name of a formula and write its actual chemical formula. So you need to be able to convert names to formulas and formulas to names. The other thing that you're going to have to do is remember in chemistry, in my class, what I used to call these were the Brinkelhoffs or the Magnificent Seven. These are your diatomic elements, okay? These are elements that they don't exist by themselves. They exist as a pair in nature. So for example, hydrogen is not H. Hydrogen gas is not H. It is diatomic. And what does di mean? Di means two. So all of these elements in nature exist as a pair. So hydrogen does not exist as H, it exists as H2. Bromine does not exist as Br by itself, it exists as Br2. So why do I call these Brinkelhoffs? Because if you spell them out, it spells Brinkelhoff. And why do I call them the Magnificent Seven? Well, it's easy. Because they start with the number 7, which is nitrogen. They draw the number 7, and there are 7 of them. So 1, 2, 3, 4, 5, 6. We got one outlier, Mr. Hydrogen over here. So those are the Magnificent Seven. So make sure you write those down or call them Brinkelhoffs so you know when you're writing these formulas which ones you need to make diatomic. All right, so we're going to take that word equation that we just looked at and we're going to turn it into a chemical equation. So get a periodic table out if you don't have one already because you're going to need that. So let's look here. This is the one we just talked about a minute ago. Solid iron and chlorine gas react to produce solid iron 3 chloride. So let's start writing these formulas down. Solid iron. So look at your periodic table. And iron is Fe. And we've said that it's solid. So to show that it's solid, we're going to put an S in parentheses next to the iron. And, who remembers how we write and in a chemical reaction? In a chemical reaction, to write and, you're going to use a plus sign. So we have solid iron and chlorine gas. Chlorine. Chlorine is Cl. But you should notice something special about Cl. Cl was one of those Magnificent Seven, one of those Brinkelhoffs over there. So Cl does not exist as Cl by itself. It exists as Cl2. That's why I said it's really important that you know those 7. Now, it's a gas. so next to it, we're going to put a G. It reacts to produce. What does that mean? When we're writing an equation, what does reacts to produce mean? That means you're going to want an arrow. And it reacts to produce solid iron 3 chloride. Well, I'm telling you that iron is Fe and it has a charge of +3. So we're going to have to remember how we wrote our formulas last quarter. So I'm going to put a +3 at the top of iron. And it's iron 3 chloride. Chlorine is not by itself here. He's with iron. So you're not going to use a 2. When you put things together in a chemical formula or in a chemical reaction, you're going to have to crisscross the charges. So what we're going to do is take this +3 from iron, and we're going to go look at chlorine on the periodic table. Chlorine is in the last column, and what you should know from last quarter is that everything in group 1 has a +1 charge. Group 2 is a +2. 3 is a +3. Then we get here to ±4, -3, -2, -1. And these guys don't like to react. They don't really have charges. They're happy the way they are. So when I go to chlorine, which is number 17, I see that chlorine has a charge of -1. So when you're writing a formula, you crisscross your charges. So I'm going to bring this 3 down as a subscript to my chlorine, and I'm going to bring a 1 down to my iron, but you should have learned from last quarter that we don't ever write the 1s. So we end up with Fe solid plus Cl2 gas goes to give FeCl3, and I told you that that was also a solid. So that's how you take those words and you go to a skeleton equation. So we're going to try another example of this. Write the skeleton equation for solid magnesium. Magnesium is Mg, and it is solid, reacting with oxygen gas. So we know that oxygen is O, but what else do we know about oxygen? We know oxygen is one of those 7 we just talked about, and it's diatomic. So he can't be alone. He has to come in a pair. So he is O2, and this is a gas. And it reacts to produce solid magnesium oxide. So when we put them together, we have to crisscross charges. We know that magnesium is Mg. So we find him on the periodic table, and he has a charge of +2. We find oxygen on the periodic table. We see that oxygen is in the group that has a charge of -2. And then we crisscross the charges, but the +2 and the -2 cancel out. And we see that it was solid. So this would be our skeleton equation for that reaction. So what we're going to do now is talk a little bit about the law of conservation of mass, because this is really, really important for everything that we're going to do the rest of this quarter. Law of conservation of mass states that whatever you start with has to equal what you end with. So in a chemical reaction, matter or mass is conserved. Okay? You can't gain or lose mass. It's always going to remain the same. So the way I say that is what you start with is going to equal what you end with. And when you're balancing, that we're talking about the number of atoms. So the number of atoms that we have on our reactant side is going to have to be equal to the number of reactants that we have on our product side. So I want to show you with an example here. I'm about to show you hydrogen gas, which is H2, plus chlorine gas, which is Cl2. Actually, let me do oxygen. Hydrogen gas plus oxygen gas goes to give water. Okay, so I want to show you what that looks like here. So we're going to do a little modeling from up front. So I'm going to call this little white set here, this white model, that's my H2. There's 2 hydrogens. I'm going to call this red set my O2. So I have H2 plus O2 going to give me H2, which means 2 H's, and an oxygen. Law of conservation of mass has to be followed here, which means if I have 2 white spheres over here, I have to have 2 over here. And what we see that that's correct. I have 2 hydrogens here, and I have 2 hydrogens here. But what you see is wrong is my oxygens. I have 2 oxygens here, but on this side, I only have 1 oxygen. So what we're about to do is do something called balancing these equations. So I have to make them equal. So I have 2 hydrogens here, 2 hydrogens here, 2 oxygens here, which means I need another oxygen. But I can't just put an oxygen out there because that's not what the reaction is. I have to put a whole nother water. So now we see I have 2 hydrogens on the reactant side, but 4 hydrogens on the product side. I have 2 oxygens as my reactants, but I also have 2 oxygens as my products. So the problem we have now are my hydrogens are not balanced. So what am I going to do? I'm going to take another hydrogen and I'm going to add it to the equation. So now I see 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. So what this tells me in a chemical formula is that I need 2 of these H2 molecules, I need 1 O2 molecule, and I'm going to get 2 waters. So there are some steps for this. The first step is you got to write the skeleton equation. Okay? So write the skeleton equation, which is what we've been working on. Then you're going to count the total number of atoms on the reactant side. Then you're going to count the total number of atoms on the product side. Then we're going to do something called add or change the coefficients to make the numbers equal. And something that I need to make sure you know is you can never ever change a subscript. Subscripts are those little numbers at the bottom. You make sure everything's written in the lowest whole number ratio and always check your work. So let's look again at some of these definitions. A subscript are these numbers at the bottom of a chemical formula. You cannot change those. That makes that chemical formula its formula. The coefficients are the numbers that are going to go in front of these chemical formulas to change how many of them there are. Like we had 2 H2 molecules here. So you're going to add and change coefficients, because you can change those, until you balance it. So let's do this one. Let's try this one. Write and balance a reaction between sodium hydroxide, which is NaOH, and calcium bromide, which is CaBr2. That 2's not there because it's a Brinkelhoff. That 2 is there because that charge of that calcium was a +2. It goes to give calcium hydroxide and sodium bromide. So now we're going to look at these. I see here I have 1 Na. Here I have 1 Na. So we're good. Here I have 1 OH, but here I have 2 OHs. I can't change a 2 here because I can't change a subscript, so I'm going to put a 2 in front of it. That's going to give me 2 Nas, but here I only have 1. So I'm going to put a coefficient of a 2 in front of there. So I have 2 Nas, 2 Nas, 2 OHs, 2 OHs, 1 Ca, 1 Ca, 2 Brs, and 2 Brs. So you've balanced that chemical equation. Now you're going to have a lot of these in those minor grades that you have to do for your packet if you're using a packet. So I want to go over your assignments for you real quick. If you are doing online learning with your teacher, this is just some review for you. They're going to have assignments for you. You make sure they're doing exactly what, you're doing exactly what they need you to do. However, if you're using the packet, I want to tell you what today will cover. Today is going to cover the minor grade, section 11.1. After today, you should be able to do that entire section. Section 11.2, we're going to cover next week. On your major grade, pull open that major grade and go through and do any that we talked about today, which should be balancing reactions, talking about products and reactants and arrows and plus signs. So go ahead and get those done. Again, in chemical equations, that 11.1 is going to look like this, where your major grade is going to look like a multiple choice test. So that was a lot, but that's all we have time for today. So I kind of hope they showed the slide on this because I love puns. I hate goodbyes. When you are gone, I'll miss you periodically. So I hope you enjoyed today. I hope you join me again next week where we're going to be talking about different types and classifications of reaction. And if you have littles in your house, go grab them because next up is going to be Miss Brittany Fillingham who's going to be doing phonics lessons. And guys, she is amazing. So stay safe and we will see you next week. Have a great one, guys.